Welcome back. I think that now it's time to work with vectors in 3D. You've seen that decomposing vectors into x and y components made it easier for you to add vectors. That is especially true when you work with vectors in 3D. In fact, you should always decompose your three-dimensional vector into x, y, and z components, and then it will be easy to add them up. But okay, in this problem, you can think of a wall, and then on the wall in the origin, you have a small hook, and there are two force vectors applied to that hook. This force here is F1, 450 newtons, and this one is F2, 600 newtons. These are the magnitudes of the two forces. But of course, just like in 2D, you also have to represent the direction of vectors in 3D somehow. And there are several ways you can do it. In the image, you see angles representing the directions of F1 and F2. However, for each vector, these angles follow a different logic, and we will cover both of them here. And then, of course, you can also represent these vectors using the XYZ components. In fact, what we need to do now, we need to find that angle gamma for F2. And then we need to decompose the F1 and F2 vectors into the XYZ components. Just like in 2D, we can use unit vectors in 3D. This is a typical XYZ coordinate frame. It's called a Cartesian coordinate frame. On the XY plane, you had the I and j unit vectors. And in this image, this would be I, and this would be j. And now in 3D, you have a third unit vector, and that's k. Its magnitude is also 1, and it points in the positive z direction. So let's say that you have a random vector a here. It has three components, ax, ay, and az. Using the unit vectors, you can represent it like this. A arrow equals ax I plus ay j plus az k. So the I unit vector is in this direction, j unit vector is in this direction, and k unit vector in this direction. Alternatively, you can represent A like this. A arrow equals, and then the three components are written in this form, or even like this. A arrow equals, and then you have a row vector, and then you put here transposed. When you add two vectors, then with these components, the logic is exactly the same like it was in 2D. Let's say that f1 vector equals 2i plus 3j plus 4k, and then f2 equals minus 2i plus 7j minus 10k. Then f1 vector plus f2 vector equals I times 2 minus 2 plus j times 3 plus 7 plus k times 4 minus 10. So f1 plus f2 equals 0i plus 10j minus 6k. If you now look at this vector a, then from the previous videos you learned that in 2D you could get the magnitude using the Pythagoras theorem. So in this case, on the xy plane, you could calculate the magnitude of the ax and ay components. We can call it a apostrophe. And so a apostrophe equals square root ax squared plus ay squared. It makes sense because you have a right triangle here. And now if you want to get the magnitude of this 3D vector a, then notice that you have a right triangle here as well. And so you would have a equals A apostrophe squared plus AZ squared. Or I can write A equals, and then I have square root here. Then instead of A apostrophe squared, I write this thing, which is this thing squared, plus AZ squared. And since you have square root here and squared here, essentially what you will have is this: AX squared plus AY squared plus AZ squared. That's the formula for the magnitude of a 3D vector. Another thing that I want to mention is that the Cartesian XYZ frame that we are using, it follows the right-hand convention. What it means is that your right-hand thumb points up in the positive Z direction. Then your other fingers are pointed in the positive X direction. And then, as you curl them, they move towards the positive Y direction. Welcome back. Let's look at this A vector again. And let me only draw AX for now. Notice that the tip of A and the tip of AX, they are located at the same X value. It means that if I draw this purple line here, then you have a tilted triangle here. And then right here, you have 90 degrees. Let's call this side A. If I take this tilted right triangle and I draw it on a 2D plane, then it looks like this. So you see, this point here, that's the origin of the coordinate frame. And then you have your AX here. Then you have your A vector here. And then this is this side A. It's this one here. This is your tilted triangle, which is a right triangle because here you have 90 degrees, which is this one here. And so obviously, this is the x-axis. And now, you have an angle here, let's call it alpha. And it's this angle here that goes from AX to A on this tilted triangle. So it's like a tilted plane. So remember, this angle here, that's your alpha. It goes from the positive x-axis till your vector A on this tilted right triangle. Similarly, we can do it with the AY component. The tip of AY and the tip of A, they have the same Y value. So I draw a line here, I'll call it B, and again, we have a tilted triangle here, and since A and AY have the same Y value, that means that you have 90 degrees here. It's a tilted right triangle. This is how it looks like in 2D. You see, you have your AY, you have your A vector, and this is your B side. And here you have 90 degrees. And of course, this point here, that's the origin of the coordinate frame. And now, I have another angle here, and I'm going to call it beta. And here, it would be this one. That's your beta. In this tilted right triangle, beta goes from the positive y-axis till your vector A. And finally, we can do the same thing with the AZ component and the A vector. Again, the tip of A and the tip of AZ, they have the same Z value. So I can connect these 2 points. I'm going to call it C. And here you have 90 degrees. In 2D, it looks like this. So it's this right triangle, and this 90 degrees here, that's this one here. And of course, this is the origin of the coordinate frame. And now, I'm going to define another angle. I'm going to call it gamma. And so this gamma, it's right here. That's your gamma. It goes from the positive z-axis till your A vector along this right triangle. And so we have defined 3 angles. Alpha, which is this one, beta, which is this one, and then gamma, which is this one. They are special angles which are called coordinate of direction angles of a Cartesian vector. If you have a three-dimensional vector, then in our right-handed Cartesian XYZ coordinate frame, you can completely describe the direction of your 3D vector using these three angles. However, if you use these angles, then there are a couple of rules that you have to keep in mind. First of all, alpha is always defined from the positive x-axis. Then beta is always defined from the positive y-axis. And gamma is always defined from the positive z-axis. That's just a convention. You never define them from the negative axis. For example, in this case, this is your y-axis, and you should not do something like this, where you define this beta angle from the negative y-axis. If you do that, then that would be wrong. You should define it from the positive y-axis. And another thing that you have to keep in mind is that alpha, beta, and gamma, they only go from 0 degrees up until 180 degrees. You don't need them to vary more, like for example till 360 degrees. That's not necessary. If you define alpha, beta, and gamma from the positive x, y, and z axis, respectively, then you can know the direction of any 3D vector, provided that these angles can vary between 0 and 180 degrees. And now, if you look at our initial problem, then you can see that this vector f2, it has these three coordinate direction angles. This one is alpha, it's 45 degrees, and you can see that it's defined from the positive x-axis. Then here you can see that you have your beta, which is 60 degrees, and it's defined from the positive y-axis. And then here you have gamma, which is defined from the positive z-axis. And here gamma is unknown, and we need to find it. But we will get there. But now, let's investigate these coordinate direction angles a bit further. If you look at these three tilted right triangles, especially if you look at their 2D drawings, then you can see that we can get some interesting relationships from there. For example, we can have cosine alpha equals ax over a, then cosine beta, that equals ay over a, and then finally cosine gamma equals az over a. Then in addition, in 3D, next to your three Cartesian unit vectors, you also have a general unit vector that points in the direction of this a vector, and that is called UA. Just like the magnitudes of ijk equal 1, also the magnitude of this unit vector in the a direction, it's also 1. Essentially, you can say that a vector equals its magnitude times this general unit vector. Or more informally, I can write it like this without the absolute signs and without the arrow. So this is the magnitude of a. And here I will multiply it by 1, but the purpose of this general unit vector is to show direction. And this unit vector, it points in the a direction. As a result, you have this vector a that points in the same direction. Also, since you know that a vector equals axi plus ayj plus azk, you already know that because this is ax here, this is ay here, and this is az here. Ax points in the I direction, ay points in the j direction and AZ points in the k direction. And then you know that the magnitude of A equals this one. And so if I write A vector over the magnitude of A vector, then I will have AX over A times I plus AY over A times J plus AZ over A times K. So this expression gives you the ratios of your A's X component and the magnitude of A, then the A's Y component and the magnitude of A, and the A's Z component and the magnitude of A. And now if I take this A magnitude and I multiply it by this one here, then you will have A times, and then all this expression, which equals this one, and so you can cancel out the magnitudes here, and that means that you are left with this expression here, which is this one here. What does it mean? It means that this one, that's your general unit vector in the A direction. That's this one here. Then this one, this is the magnitude of your A vector. And then if you multiply them together, then you get this expression, which is your A vector, this one here. So now you know how this general unit vector is defined. Now note that the magnitude of this general unit vector also needs to be 1, so we can check that. The magnitude of the general unit vector, or I will simply write it like this, I will square all its I, j, and k components, and then I square root it. Then I can write it down like this. This is the common denominator. Now if A equals this is the magnitude, then if I square it, then I also square the other side, and so it will simply be ax squared plus ay squared plus az squared. And so as you can see, my expression becomes like this, and I have the same numerator and denominator. So here I have 1, so I'm left with 1 to the power of 1/2, which is 1. And that's the magnitude of my general unit vector. For example, if I have a force vector that equals this expression, then the magnitude of this force vector, it would be this one. In other words, it will be square root 29 newtons. So the general unit vector F that points in the direction of this F vector, it's 2 over square root of 29 times I, then 3 over square root of 29 times j, and then 4 over square root of 29 times k. And then the magnitude of this F unit vector, it's this one, which will give you square root of 29 over 29, which gives you 1. And also, just like you had it with this formula here, in the same way we can write F vector equals the magnitude of F vector times the general unit vector in the F direction. That's the magnitude of F, that's the general unit vector in the F direction. The magnitudes cancel out, and you're left with your original F vector. But now, if this is your general unit vector, then remember that AX over A, that's cosine alpha, AY over A, that's cosine beta, and AZ over A, that's cosine gamma. We saw that here. You see, cosine alpha, AX over A, cosine beta, AY over A, and cosine gamma, AZ over A. That means that this general unit vector A, it can be written like this: cosine alpha times I, cosine beta times j, and then cosine gamma times k. That also means that A vector equals the magnitude of A vector times this unit vector, it will be a times cosine alpha times I, then a times cosine beta times j, and then a times cosine gamma times k. And that means that this part, that's ax, this part is ay, and this part is az. And so from these derivations you can see that once you know the x component of your vector and the vector magnitude, you can calculate your alpha, and the same thing here, once you have the y component of your vector and the vector magnitude, you can get your beta, and then if you have your az and a, you can get your gamma. So these are important relationships that you should keep in mind when you solve problems with coordinate direction angles. And finally, we saw that the magnitude of this general unit vector equals 1. And so if you take this form and you calculate its magnitude, then essentially you will have this relationship here. So square root, and you take these three components and you square them inside your square root, and that has to equal 1. And if I square the magnitude, then I will put 2 here as well, and also 1 to the power of 2. And so I will have this relationship: cosine alpha squared plus cosine beta squared plus cosine gamma squared, and it equals 1. And this is also a very interesting result, because here, if you know two angles, let's say beta and gamma, then you can calculate the third angle, alpha. So all these results, they are tools to work with coordinate direction angles and describe the direction of vectors. And now you can already solve half of this problem that you have here. You have your f2 vector, you have your alpha, you have your beta, and you can now calculate your gamma. But before we do that, we still need a little bit of more knowledge for this f1 vector. Thank you very much.